Hello and welcome to another SolidWorks how-to video. This video is all about the basics of assembly modeling. So we're going to take a couple of parts in SolidWorks and basically stick them together, talk about some of the best practices for how to do that, some of the things we think about, and sort of stick for now with a basic assembly with the sort of normal-ish constraints, quote unquote. So to start out, we're just going to sort of bolt two plates together. And to do that, I've already created two plates. This one here is just a plate with some countersunk holes in it for a 1/4 20 flathead screw. To get these over here on the feature manager, I've just used the hole wizard. We've talked about the hole wizard in previous videos, but I used the hole wizard to create 1/4 inch through holes with an automatic countersink and an 82-degree angle for a sort of a standard UNC 1/4 20 screw. Now, I've also got open in SolidWorks. Something we haven't talked about in my previous videos is SolidWorks has the ability to open multiple models at the same time. To sort of switch between those, I can hit Control Tab, and it brings up a list of all the open documents, and I can just hold down Control and keep hitting Tab and sort of cycle through them. So we have that top plate. I've created a similar plate with the same dimensions. And again, I use the hole wizard, but in this case, I use the hole wizard to create 1/4 20 tapped holes to accept the screw threads. And then I have also modeled a 1/4 20 screw. And again, I recommend you model your screws. Well, first of all, I recommend you use screws. They can be a significant contributor to weight in assemblies, especially if we're talking about 3D printed components. If we have to screw some things together, right, a steel screw is a significant amount of weight the compared to the PLA material that we might be, 3D printing with. So I recommend you model your screws. I do not recommend you, however, download them directly from like McMaster Car because those typically include fully modeled screw threads. And as we get into more and more complex assemblies where we're dealing with hundreds of screws, that's a lot of data for SolidWorks to sort of process in real time. And that's where we get some hefty slowdowns in the software with bigger assemblies, especially on like right now, I'm modeling on a laptop. SolidWorks generally doesn't require a lot of horsepower to do what it does, but it really does require that horsepower when we start to get into all of the surfaces involved with like hundreds of screws that are all showing perfectly modeled threads. So in this case, I've modeled it the way I recommended in previous videos, where I've just the major diameter is a 1/4 inch because it's a 1/4 20 screw. And I've added an annotation here, the dotted line for a cosmetic thread. So later on, if I do need to throw this into a drawing, I can throw a note on there that'll automatically say, 1/4 20 thread. So those are the three parts. Again, Control Tab will let me cycle through them and show which ones I have open. I'm going to start with the plate with the threads in it as sort of the base of my assembly. This will be the first part I put into my assembly. Now, there are a couple of ways to actually create an assembly. First, we can create an assembly the same way we would a new part. So up here above the ribbon, sort of next to the SolidWorks title, I can create new and click over here on assembly and create an assembly that way. Somewhat faster, and it's personal preference, and you're welcome to mix and match it. It doesn't really make any difference whatsoever. Another way to create an assembly directly from this part, like I know this part is going to be the first part I put in the assembly. On the new dialog, there's a drop down, and I can click that drop down and jump right to make assembly from part. So I'm going to click that one, and SolidWorks will automatically, without a pop-up, it'll sit and process for a minute, but it will automatically create an assembly. And I have a begin assembly dialog over here on the left where my feature manager would be. But it wants me to basically select out of the open files that I have right now, which part do I want to drop in first? Because I clicked create create assembly from part, that threaded plate is automatically selected. So I'm just going to out here somewhere in space, just click once, and it will automatically drop that part. Now, when we look over at the feature manager, I've got the threaded plate dropped in, and there's an F here in parentheses. That F stands for fixed. The first part that we drop into an assembly in the SolidWorks is automatically defined as fixed. SolidWorks locks it in place so that it absolutely cannot move. In fact, if I click and drag, I believe, yep, I'll get a pop-up that says this component is fixed. It cannot be moved, right? That's what the F stands for. However, there's a problem with that and just relying on that because I just clicked randomly in my window. I have absolutely no idea right now where 0, 0, where the origin is at. That's a problem. I want my assembly somewhat related to the origin. And if I click here in the feature tree, I can actually select the origin and you see it pop up sort of in my lower right. That's the blue dot here. That's the origin of the assembly, right? And if I rotate the model a little, you can see it's out there in space and it doesn't really have anything to do with the parts that we're putting in. That can be a problem. I really want that first part to be referenced to the origin in some way. The easiest way to do that is to use the fixed mate. We call them mates, not constraints in when we're dealing with assemblies, but use the fixed mate, but in a more sort of controlled way than the automatic one that SolidWorks throws in when we just drop the part in the window. So to get started, I need to first break this mate. I need to undo the fact that SolidWorks fixed this part. So I'm going to right click on my threaded plate in the feature manager. And I'm going to come down here, sort of in the top third where it says float. And I'm going to float that part. Now the F has changed to a minus sign. In an assembly, the minus sign is similar to the blue lines we would see in a sketch. The minus sign means we are under constrained. This part can now move. It can move up and down. It can move side to side, right? There's not really a good way to rotate it, but it can also rotate. Every three-dimensional part on an XYZ coordinate system has what we call 6 degrees of freedom. It can move in a straight line along X. That's 1. It can move in a straight line along Y. That's 2. It can move in a straight line along Z. That's 3. And then I don't have a tool in SolidWorks to really rotate it this way, but it can also rotate around each one of those axes. So that's 3 more for a total of 6 degrees of freedom. Our goal, say 90% of the time in assemblies, is to completely constrain these parts so that all 6 degrees of freedom are accounted for. We don't typically want our parts to be able to move at all. Now, there are some exceptions. For instance, let's say I was modeling an air cylinder. I may want that air cylinder to actually be able to extend and retract, in which case I would not lock down one of those dimensions to allow the rod to slide in and out of the air cylinder. Pardon me. So that's an exception, but I will say that most of the time, again, as a guess, something like 90% of the time, we're going to want to fully constrain these parts so that they can't move at all. So that they can't translate, move in a straight line or rotate. But for this first part, it's probably the easiest one because we do want it to be fixed. We just want it to be fixed with reference to the assembly's origin, to the assembly's 0, 0. So to do that, I'm going to expand in the feature manager the part. And if I expand that, I get to all of the same features that I had before. I can get to the individual planes that belong to that part. Notice if I'm going to actually show this and see if it demonstrates well. I'm going to actually show the front plane of the part, and then I'm going to show the front plane of the assembly. So if I show both, okay, they don't actually show up. So it didn't end up showing well. The joy of stream of consciousness recording, right? But again, I can move this all around. So it's really right now, it has no reference to the origin at all. To fix that, if I come up here to my ribbon, and I'm going to click on the assembly tab on the ribbon, and I'm going to click on mate. When we want to constrain these things, lock them down, everything we do is we're going to be adding a mate. So I'm going to mate, and it pops up here now where the feature manager was. It wants me to select some things. The first thing it wants me to select what features of this model that I want to mate. In this case, I don't want to mate features. I want to mate the origin of the assembly. So that's the first thing I'm going to click in my tree here, which is now in my model window. I'm going to click the origin of the assembly, and it pops in here for mate selection. and I'm going to click the origin of the part. Notice the part slid right out of view. I'll fix that in just a moment. SolidWorks assumes that I want a coincident mate, which, I do in this case. And it also wants to align the axes, which again, for this very first one, at least, that is exactly what I want to do. What that'll do is with one mate, it will lock it down to 0, 0, and it will align X, Y, and Z. So it stops it from translating and it stops it from rotating. So when I click accept, the green check mark, either here or up here, or even up in the upper right, there's a couple of places in SolidWorks I can always accept. But when I accept that mate, I'm going to click the green checkbox again to get rid of the mate window. Now, I can scroll over. I have a pretty good idea of where this model is. One quick way, because occasionally as we're rotating things and we're mating and because we just drop things sort of randomly in space, one quick way to get our model back in our view is up here in these little view icons we have above our model space. The very first one is zoom to fit. So if I click that, no matter where the model is, it's going to automatically center my camera on it. So I can find it sort of immediately. I could, again, zoom out way, find it if it was way over here, zoom back in. But the quick way is to just zoom to fit and it'll pop it right in. Now, if I select the origin again, we can see that the origin of my part and the origin of the assembly are lined up. And so now are all of the planes. So right and right, top and top, they are all lined up. This part now cannot move. And I can tell that also because the little minus sign in parentheses is gone here. There's nothing ahead of this part number, which means this part is fully locked down. And again, if I try to drag it, I get the little pop-up that says this is fully defined. It cannot move. And that's what I want. I could leave it alone when I drop it in, but again, that origin then of the assembly is just sort of floating out in space at random, and that I don't like. So that's sort of how we lock down this first part. That's the easiest way, anyway, to lock down this first part. So now I need to drop in the plate with countersunk holes on it, the plate that the screws are going to kind of go through. So up here on the assembly part of the ribbon, I'm going to click Insert Components. And again, it shows me all the parts that I have open. If I didn't have them open, I can always hit Browse and let it browse, my file system on the computer to find the part. But since I have it open, this one is called Clearance Plate. I can click that. And because it's the second part now, I didn't get this the first time. When I come over here, I'm not clicking anything, but I get a preview of the part now and where it's going to drop. So really at this point, you just drop it anywhere. It helps to try to be close to where you want to be in the end, but it doesn't really matter because our mates are going to automatically lock it in place. So I'm just going to drop it in the window. And if I zoom out a little and start to rotate, you can see it truly is kind of, randomly dropped in there. So now the trick with assemblies in general is we want to sort of think about how these things are actually physically locked down. We're not technically, as we build this assembly out, we are not locking these things together with a bolt. We're going to lock them together and then add the bolt. But we know that physically in the real world, the bolt will be the thing that is constraining these together. So it helps to get efficient assembly models and the proper mates. It helps to think about physically what is actually locking these things down. For instance, I can, if I select mate, right, and if I select as my mate selections here in the blue box on the left, if I select these two faces, the face on this top plate and the face on this bottom plate, SolidWorks will default to make them coincident. And they will be lined up. If I rotate a little bit, they're lined up now, right? We can fix the fact that they overlap here later in a second, but they're lined up. And if I accept this, accept everything, get out. And if I try to drag, I can drag in Z and I can drag in Y, but no matter what I do, even if they're in, right, no matter what I do, no matter any of this dragging, I cannot make them no longer lined up. They are mated. They are coincident. They'll be in the same plane forever. The problem with doing it this way in this particular setup is in the physical world, like if these were real parts, it is not just a random chance that these two are lined up. It is the bolt that is making these things line up. So a better choice, I'm going to select over here. I can make my mates category bigger, expand it out. I can select that coincident mate and I'm going to delete it. And it warns me, yes, right. So I deleted it. Now the thing is free. I can make them misaligned again. The bolt is the thing doing the lining up in this case. So it is best to select the bolt holes and use those as my mates. So to do that, I'm actually going to select this diameter and this diameter. Control click to select both. I'm going to click mate, and SolidWorks automatically assumes I want a concentric mate, which is what I want, right? There are other options. I could set them to be tangent, and if we zoom, notice tangent means the two circles will be tangent, but that doesn't really work. There are times when we could want to do that, but we want them to be concentric because when we put a bolt in here, they will be, minus some tolerances, they will be concentric. So I'm going to go ahead and accept that. And I'm going to get out of the mate dialog. So I'm now locked to that bolt hole. Those two holes in these two plates will forever be concentric. If I drag, notice I can rotate, and I'm even moving a little bit in Z as I move my mouse. Right now I'm embedded one part into the other, and I've rotated these other holes out of position, but the hole that I mated is still concentric. It's still in alignment, which is what I wanted. Right? So I'm going to deselect everything. Now I am going to select one of the other holes. It doesn't really matter for this particular bolt pattern which, but let's pick this opposite sort of corner one. I'm going to select the hole inside, and I'm going to select the hole in the top plate, and I'm going to hit mate again. And again, it's going to assume that I want it to be concentric, right? And so if I accept and accept, I'm now locked. I can't rotate anymore as I drag. Notice I'm still dragging in Z, right? I have not done anything to stop this part from moving up and down. But because I now have two holes locked to be concentric, I can't rotate it anymore. So I haven't told it that these faces need to be in line. I haven't told it that these faces need to be in line. I'm letting the bolt holes, the fact that these holes have to be lined up, handle my alignment. Now, there is one thing to note. I'm going to go ahead and delete this second concentric constraint. There is one thing to note, and I'm going to drag this guy so that it's rotated sort of out of whack. If I click on this first concentric constraint, and in the little context thing that pops up, if I edit that feature, there's an option under concentric that says lock rotation. That's a tricky one because lock rotation is going to lock the part wherever it is. That may be okay if the part were already lined up. It's not great though because we're not technically using another hole to line it up, but lock rotation might be okay. But if we're out of whack like we were when I started, and I lock rotation, right? I'm going to accept, and I'm going to get out of mate by accepting again. I can't rotate anymore. Rotation is locked, but I'm sort of in a random spot because I locked it where I left off, intentionally rotating it out of alignment. So it is much better rather than locking rotation to actually use that second hole. So I'm going to edit this mate again. I'm going to undo that lock rotation, accept. Now I don't have to accept to get out of mate. I can just make selections to add a mate. So I'm going to select that hole again. Notice it goes transparent. The first selection, the part that you select first, always goes transparent so you can select the other part that you want to mate it to. So right through this block now, I can select that hole, even though I couldn't see it a second ago. So I'm going to select that diameter. It aligns it because it assumes I want it concentric. Again, I could do a tangent. And if I rotate a little bit, you can see that the circles, are locked down to be tangent, but it's a bolt hole. I want it concentric. So I'm going to accept that, right? And now I can't rotate again, but I can still move in Z. So then the last step to sort of lock this top plate down is I'm going to select this face and the face that it's going to sort of clamp to. And in SolidWorks, again, assumes I want a coincident constraint. And that's actually what I do want. I could, in some instances, you may want to set a distance. So if I select distance, it sort of automatically defaults to the distance they were apart when I hit mate in the first place. If I change this to like 0.5, right, I can accept that. In these parts, I'll accept to get out of the mate. Notice my minus sign went away. So this plate is locked down now. I can click and I can't drag. Right? I get the little pop-ups because I can't move it. And they are forever now a half an inch apart. That is a thing that could be useful, sometimes too, that distance mate. But again, in this case, it is not a distance, right? We're going to clamp these things together with bolts. So I'm going to edit my mate. I'm going to not select distance, and I'm just going to hit coincident. Let them be coincident, accept. Now I've got the coincident in there. The minus sign is gone. If I drag, I can verify, right? It says it is fully constrained. So this part now is locked down. It cannot move. So what's left is the screw, right? I need screws to sort of lock this thing together. So again, up on the ribbon, I am going to insert a component. I've already got the screw open. So I'm going to drop this screw in there. Now, I have 4 screws that I need to place. If I come over here and I just drop this screw, my little insert window goes away and I have to come back up to insert components, select the screw and do that 4 more times. When I have multiple copies of the same part to install, or if I wanted to drop all of the screws and this top plate in at once, the way that I can do that is this little pin icon right here. If I click that first, that is going to leave the insert component option open until I click the green check mark. So I can drop a screw. By clicking, it stays open. So I can drop a 3rd screw and it stays open and I can click to drop the 4th screw. Now, when I come over here and click the green check mark, it goes away and I've got 4 screws in place. Now, they're randomly placed because, that's what I told them to be. I haven't defined any mates yet. But that's how I can get multiple copies of the same part into an assembly. So to start constraining these, it doesn't really matter what order they go in or what hole, right? They're all screws, they're all the same part. So I'm going to go and select the outer diameter of the thread into the inner diameter of this hole. And I'm going to come up to the ribbon and click mate. Again, SolidWorks assumes concentric, which they're screws. So that is exactly what I want. I'm going to click OK. And this screw, it doesn't really matter whether I select this diameter in the countersunk hole or if I select the threaded diameter because they are concentric. So for all intents and purposes, as far as at least X, Y, and Z coordinates, they're in the same spot. So I'm going to select the threaded diameter just to show that it doesn't matter. It's still lined up. And let's accept and drag this screw up in Z a little bit. It's still lined up with the hole. It's still in the middle because they're the same. So it doesn't really matter in these instances which diameter we grab. So again, thread diameter, we'll just grab the easy one because otherwise I have to rotate and, sort of, drag the mouse in here. We'll just click the one that's easy, right? Get it concentric, accept, click this one, get it concentric, and accept. So now all the holes are lined up with their respective screw holes, or all the screws are lined up with their respective screw holes. Now, I need to get these things so that they're actually, representing clamped down. Let me close the mate window by accepting. I could just drag and get them down, but that doesn't actually, mimic the reality because when it comes right down to it in SolidWorks, I can click this and drag it all the way through the part, right? I'm now, burying metal inside of metal, which really doesn't work. So I need to mate these. And SolidWorks, when I click mate, this coincident mate does not necessarily have to be flat surfaces. And because these are 82-degree screws, this angle on the screw head is 82 degrees, and this countersink is 82 degrees, I can click this surface on the screw and I can click this surface in the countersink, and SolidWorks will automatically make them coincident because they are I should say mateable, if that's even a word, surfaces. Because they have the same angle, they can be made coincident. So SolidWorks will do that for us. It takes right care of it. So if I accept that, I can do the same for all of these screws. Select the taper on the screw and the countersink and accept. And if you'll notice, you see sort of these discolorations. That's because SolidWorks models things so that they are truly round. Like mathematically, if we were to look at the programming that is running SolidWorks, these holes truly are round. However, when it renders it for display in our computer, it actually displays it as facets, right? If you can sort of see straight lines in this area, especially on this hole, it's sort of straight line, straight line. That's just a trick of rendering. Mathematically, as far as SolidWorks is concerned, these things are perfectly round. These discolorations that you see are the fact that the rendered flats on the countersink do not perfectly line up with the rendered flats on the screw. So we're seeing an overlap. And that could be a good indication, especially in this case, that we are truly mated. Those two surfaces are in perfect contact when we see that. So just a little tip there and sort of what's going on under the hood in SolidWorks. So on the last screw, click the taper on the screw and the countersink. It drops it in, coincident. I'm going to accept it and accept it. So we now have our screws in place. But if we look at the feature manager, we have minuses in front of every single screw. That is because we have set them to be concentric, which sort of locked down their X and Y translation, so we can't drag them across in either direction. The tapers locked in our Z, so we can't pull them out of the hole, but we haven't done anything to sort of lock down their rotation, right? I can still rotate them. And at this point, it would be perfectly okay to just leave it because at the end of the day, we're just representing that there are screws in these holes and we don't really care, where they land up rotationally. It doesn't matter. But it is good practice to get into to try to lock down every component we can. So we should look at ways to lock these screws down rotationally, get rid of those minus signs, make them fully constrained. To do that, again, we're going to go into mate. And notice whenever SolidWorks opens sort of a tool window over here on the left, replaces our feature tree, it pulls a feature manager into the model window right here where it says assembly one. If I expand that, that's the same as my feature manager. So I don't have to, I could go back and forth between the feature manager and the three, but I don't have to because it's given me another feature manager over here. So the other thing to note is when we are mating, I do not, just like in the beginnings, right? We've done this. The origin is technically not a feature of our model, right? It's just the coordinate system. It's just 0, 0. I can do that with other things. For instance, I could do that with other things that aren't part of the model. For instance, on my screw, these planes are technically not a part of the model, right? They're sort of theoretical planes. They exist in the X, Y, and Z directions. But I can use them to mate things. For instance, I'm going to click this front plane and I'm going to go to my assemblies front plane and click it. And notice the screw rotated. And now if I accept that first screw, the minus sign has disappeared because now I'm fully locked down. And again, I get that tool tip that says I can't move it because I have now told that front plane of the screw to always be parallel with the front plane of the entire assembly. And if I click this, notice it's a parallel name here. Edit that feature so you can see it automatically assumed parallel. I could also click perpendicular. Notice it rotated 90 degrees. That way it'll lock it down so it's always 90 degrees to the front plane. Coincident should throw an error, right? The red X here is the symbol that it's an error. I can make them coincident if I had not already made them concentric. I could line up so these planes are on top of each other. I can't do that because I've already told it it has to be concentric with the hole that it's sitting in. So it can't actually move it over here where it would need to go for coincident. So I'm going to leave it at parallel, right? My red X goes away, the error, it's happy. I'm going to accept and accept to get out. And again, notice that the minus sign is gone. Shrink that down a little. The minus sign's gone. That screw is locked down. So I'm going to mate, and I'm just going to repeat that process for the other screws by selecting the front plane of the screw and the front plane of the model, or the assembly rather, parallel. Notice the screw rotated so that it'll be parallel. I can accept. I don't have to accept again. I can just keep mating things. So I'm going to shrink this. Now, important to note, this feature manager that's in our model window here does not update the minus sign as we go. We have to wait until the end, and then the feature manager on the left will update. So we're on this screw. It can be tricky when we've got a lot of things and we're questioning, well, did I really lock that one down? That's when it can get tricky. More of a nuisance really than a problem. But if we mate that, shrink this screw, and then the last screw, front plane, and assembly front plane, right? That one didn't have to rotate very far. It was already pretty close to alignment. Accept that, accept again. And now I've updated so that all 4 screws are missing their minus signs. This minus sign showed back up, but it's still locked down. That's just a trick of SolidWorks. Sometimes we can force things like that to go away. Up here on our file tree, or above the ribbon, I should say, the file menu above the ribbon, there's a stoplight looking icon that's called rebuild. If I click that, notice that the minus sign over here on the clearance plate went away. So rebuild can help sort of force SolidWorks through some of those visual type glitches, when they happen. But we know that since we followed the right steps and locked it down in sort of a sequential way, that the plate was already constrained, even if it was still showing a minus sign. That was just sort of a nuisance visual glitch. So that is a very brief overview, sort of the basics of the thought process of how we build these assemblies. Remember, the key takeaway is to think about, even though as far as SolidWorks is concerned, we didn't use these screws to clamp these together. We designed our mates in such a way to mimic the real world so that it's acting as if those screws are clamping the plates together. So again, thank you for watching, and I look forward to seeing you in another SolidWorks how-to video in the future.